Good morning. Today, I'd like to continue talking about flux. This time, I want to think about a cube of length L in all three dimensions. If the amount of matter inside the cube changes, then it must be that there is a net outward flow of material or a net inward flow of material. What I'm going to do is I'm going to think about this still in the Newtonian sense, although I'll put in some side comments about dot products and things. The cube is going to have six sides, each one of which is a square of dimensions L by L. These six sides can be broken up into three pairs of parallel sides. I'm going to think about one such set of sides. I'm going to imagine taking a pair of such sides and splitting them up into very small pieces. I'll think of the little bit of area that goes with these pieces as being chunk of area. Even though dust travels in parallel lines, it is not necessarily true that a dust particle entering the cube through this bit of the surface exits the cube out of this piece, because the particles may well not be moving parallel to the normal direction of the two planes. It's entirely possible that a dust particle could enter through this small piece of this square and exit through the top of the cube, missing this side altogether. It's possible that a dust particle could enter the cube through the bottom of it and exit through this piece of area that we're looking at. I'm going to think of taking these two congruent squares and chopping them up into the same sized pieces. I'll think of the area of chunk number I of the square as being delta A number I. I'm going to let material flow through each one of these two squares. I'll call a representative point in this square x equal AI, y equal BI, z equal CI. Here, I'll have the same coordinates except only the x coordinate has changed. I'll call the point here P and the point here Q. I'm thinking of particles that are flowing more or less to the right. So flowing inwards per amount of area per amount of time, I'll have the mass density times the velocity vector evaluated at point P. The velocity vector for dust is constant. The density need not be, though. In more general situations, the velocity vector itself need not be a constant, but for dust it is. This is the amount of material that flows into the cube through this part of the surface per area per time. Likewise, the amount that flows outward is given by the same kind of quantity, except evaluated at point Q instead of point P. The change in mass will be the integral over the square, which I've very carefully rigged to be congruent for both of these two pieces, of the amount that flows in minus the amount that flows out. Based on our previous ideas, if within each of these two faces of the cube I select small squares of area delta AI, which in this case is delta yi times delta zi, we can figure out how much material flows into the cube through this small piece of this face of the cube in this way. Also, we can figure out how much material flows outward in an amount of time delta t per area delta yi delta zi, in minus out can easily be manipulated into this form. If I calculate the difference in minus out, a little bit of algebra will show that it's equal to this quantity. The reason that I brought the minus sign out front is so that this makes it more amenable to saying that by the mean value theorem, this fraction is a value of the partial derivative with respect to x of rho times the velocity. It is that partial derivative evaluated at y equals bi, z equals ci, and x equals alpha I, where alpha I is some number between a and a plus L. This is the contribution to the change in mass across surfaces of constant x. However, there are also surfaces of constant y and of constant z. Exactly similar arguments show that they will produce similar contributions. This gives me an estimate for the total rate of change of mass within the cube. Alpha I is between AI and AI plus L. Beta I is between BI and BI plus L. Likewise, gamma I is between CI and CI plus L. The total change in mass within the cube in time delta t is then given by this quantity. I've omitted the locations at which these partial derivatives are being evaluated because in a moment I'm going to take the limit as the size of the cube tends to 0, and it's not going to matter anyway. In ordinary vector calculus, the quantity that's left inside the integral is called the divergence of rho times v, and I'm already thinking of making the cube very small so that the locations at which I evaluate the partial derivatives might as well be more or less thought of at the same point. In fact, I'm going to make the size of the cube extremely small, but not 0. With this thought, I can think of the change in mass during time delta t as being the negative of L cubed delta t times the divergence of this mass density flux vector. Notice L cubed is the volume of the cube. If I divide mass by volume, I'll get density. So finally, divide both sides by delta t, take the limit as delta t tends to 0, and we find out that the rate of change of density within the cube with respect to time is the negative of the divergence of this flux vector, which, if you felt like it, you could write in this form. Compare this to this equation. This is the classical equation of continuity. The sigma represents the rate at which particles are being created or destroyed. So in our case, this quantity being equal to 0 means that particles are conserved. Since all the particles carry the same energy and momentum, this means this equation is a very fancy way of describing the fact that energy and momentum are conserved. This is going to turn out to be important when we think about the field equations. At the moment, though, This is a little bit unsatisfactory from a relativistic point of view. The space derivatives are partial derivatives, while the other derivative, d rho d tau, is the usual kind of derivative. Since we know that space and time are linked together, we already know that this is not altogether satisfactory. Also, the things you're taking derivatives of here are densities multiplied by components of the velocity vector. Here, there is apparently no velocity vector component to go with that. So this is not satisfactory as such. In an upcoming video, we'll look into what we ought to do to make this a proper relativistic equation, special relativistic, that is, and then what should we do to turn it into a proper general relativistic equation. Until then, I hope everybody has a good day. I'll talk to you again soon.